Hi students, in this session I want to discuss about the electronic configurations of atom. So to write the electronic configuration of the atoms, you have to follow some rules. So under that first rule is IPU principles. This rule states that in the ground state of the atom, electron enters into various available orbital in the increasing order of their energies. Okay. So now how to explain about the IPU principles here? Here suppose we know that in the K shell there are only one subshell, that is called 1s. Next L shell has 2s 2p subshell. Next 3s 3p 3d subshell. Next 4s 4p 4d 4f subshell. Next 5s 5p 5d 5f. Continue 6s 6p 6d. Next continue 7s 7p 7d, etc. Continue. Here the first energy level 1s, next 2s, next 2p 3s. So electron first enters the 1s, next 2s, next 2p, next 3s, next 3p go for the 4s, next one electron enters the 3d 4p 5s, next electron enters the 4d 5p 6s. This rule is followed here. First 1s, next 2s, next 2p 3s, 3s. This rule is first it comes down 1s 2s 2p 3s 3p 4s, next 3d 4s. If suppose if we take as example sodium, atomic number of sodium is 11. So first orbital is 1s, next is 2s, next is 2p, next 3s. Continue, next 3p. So atomic number 11 means you have to write the configuration. So here 2, here 2, here 6, here 1 is enough. Total atomic number 11, 1s2, 2s2, 2p6, 3s. Go for the carbon, next elements I go for the chlorine, atomic number 17. First write orbitals. So here 1s, next 2s, next 2p, next 3s, next 3p, next 4s. Continue this way. So fill up the electron 2, 2, 6, 2, 5, 10, 17. Yes, correct. Go for the next elements, manganese, atomic number 25. It can be written as first 1s, next 2s, next 2p, okay, next 3s, next 3p, okay, next 3p, next about the 4s, and here next 4s, but here electron enter 3d, next 4s, okay, 4s, electron enters the 4s, next 3d, okay, next 3d. So 25, 2, 2, 6, 2, 6, 18 to 25, 25 is correct. But while writing this configuration, we can write as 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 3d5, 4s2. In this pattern we can written, because this is a K shell, it's a L shell, it's M shell, next N shell. So but this filling of electron takes place according to this principle. The principle states that in the ground state of the atom, electron enters into various available orbital in the increasing order of energy. In the case of the sodium, Electron first enters the 1s orbital because its energy is least. Next enters the 2s. Next enters the 2p. Next enters the 3s. This order is a follow. If you go for the chlorine, first electron enters the 1s, next 2s, next 2p, next 3s, next 3p. This order is a followed. So this is a way of filling the electron in a different orbital. But filling of electron takes place according to this principle, and this principle statement you remember. The statement is, in the ground state of the atom, electron enters into various available orbital in the increasing order of their energy. So this is a filling of electron totally. You have to follow the output principles. Next, Pauli's exclusion principle. This principle states that no two electron can have same set of values for the 4 quantum numbers. First I take an example for this one. For example, 1s orbital. In 1s orbital, maximum number of electron accommodate is 2. There are 2 electrons can accommodated in the s orbital, maximum. Now there are 2 electrons are there. The 2 electron have opposite spin. One electron spin upward direction, another electron spin downwards direction, upward spin, different directions. So here just I can write the quantum numbers, n, l, m and s. There are 2 electron. This is a 1 electron. It's a second electron. There are 2 electron representation, one first electrons or second electron. For the first electron, what's the value of n? 1. For second electrons also, value of n equal to 1. Both values are the same. Principal quantum number 1. n equal to 1 means l equal to 0 because s orbital l equal to 0. For second electrons also, l equal to 0. m value 0 because l equal to 0 means m also 0. Here also 0. But spin quantum number for 1 electron plus half, for second electron minus half. Here first 3 quantum numbers are the same for the 2 electron. n, l, m are the same, but s value different. It is known as the Pauli's exclusive principle. The statement is, no two electron can have same set of values for the 4 quantum number. Means for the 2 electron, 4 quantum numbers values are not same. Among the 4 quantum number, any one of the quantum number must be different for the 2 electron is known as the Pauli's exclusion principle. So statement, no 2 electron in an atom can have same set of values of all the 4 quantum number. Means among the 4 quantum number, any one of the quantum number must be different for the 2 electron. Is called Pauli's exclusive principle. I take one more example for this case. For example, if you go for the 2s orbital, actually you know that maximum number of electron present in the s orbital is 2. Here 2, maximum electron 2. So values of this one, n, l, m and s. So n value, there are 2 electrons. This is the first electron, it's the second electron. What's the value of n? 2. Here also for the second electron also n value 2. L value 0. Here also 0 because yes, m value 0. Here also 0. Spin quantum number for first electron plus half, for second electron minus half. This is a different. First 3 quantum numbers are the same, but 4th quantum numbers are different. So this is called a Pauli's exclusion principle. I go for next rule, Hund's rules of maximum multiplicity. Actually, this rule states that electron pairing do not take place in the degenerated orbital until all the orbitals have singly occupied. Here, first example, suppose take as example oxygen, atomic number 8. Its configuration is 1s2, 2s2, 2p4. Okay. So now here these two are 2s and 2p is outermost shell, but s orbital has only one orbital. This is a box diagram. So 2s orbital has only one orbital. That's why two electrons are present. These two electrons occupying this orbital with opposite spin. P orbital. There are three orientation for the p orbital: px, py, and pz. This is a px. This is a py. This is a pz. Different. But now, how to fill up the electron? Because px, py, pz are called a degenerated orbital. It's called generator. What is mean degenerate orbital? Orbital having the same energy is called a degenerated orbital. Here these three are called degenerated orbital because energies are the same. Now there are 4 electrons are there. You have to go for the filling the electron. How to fill up the electrons here? So first all the orbitals are singly occupied. Here 1, singly occupied. 4th electron enters any one of this one enters here, P or maybe Py or Pz, no problem. First all the orbitals are singly occupied. Afterwards pairing of electron takes place. That's called a Hund's rule of maximum multiplicity. The rule states that among the orbitals of the same energy, electron do not pair until all the orbitals have a singly occupied. But this rule is applicable for only p, d and f orbital. But s orbital, this rule is not applicable because s orbital have only one orbital. But p 3, next d 5, f 7. Okay, I take one more example for this case. The nitrogen as an example. Nitrogen atomic number 7. If you go for the configurations of this one is 1s2, 2s2, 2p3. Here 2s okay, no problem. Only one orientation, sir. Only one orbital. There are 2 electrons can be accommodated. It's correct. 2p. Here 1, 2. Okay, how to fill up the electron? Here this is represented as a px, py, pz. How to fill up the electrons here? There are 3 electrons are present here. So here 1, here 1, here 1. P3. Okay, this is a 2s. I go for this is a filling here. First all the orbitals are singly occupied. Then electron go for the pairing. Okay, go for the next example. Manganese. Atomic number 25. I can write configuration this way: 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2. Okay, here this is comes under the K shell, L shell, M shell, next N shell. So otherwise we can also written as this one here 4s2, 3d5. Here both are the outermost shell, 3d as well as 4s, both are the outermost shell here. I take a 4s, no problem. 4s no problem, but a 3d there are 5 orientation. 5 orientation, we know that they are represented as a dxy, dyz, dxz, dx square minus y square and dz square. So how to fill up the electrons here? This is the questions here. First all the orbitals are singly occupied. If it's extra electron, they get the pairing, but here no extra electron. Okay, this is a way of filling the electron. So this is called Hund's rules of maximum multiplicity. The rule states that no electron pairing takes place in a degenerated orbital. Degenerated orbital means same energy to the same subshell until all the orbitals of a given subshells are singly occupied. If all the orbitals are singly occupied, then electron pairing takes place. This is called a Hund's rule of maximum multiplicity. Next is N plus L rules. here among the two orbital, one orbital having higher value for n, that has more energy. You suppose there are two orbitals given to you. For example, 4s is given and 3p is given, or 4d is given. Which is the higher energy? This is decided on the basis of a n plus L rule. So here for a 4s orbital, n equal to 4, L equal to 0, s orbital L equal to 0. So n plus L is equal to 4 plus 0 is equal to 4. For a 4d orbital, n equal to 4, L equal to 2. So n plus L is equal to 4 plus 2, it is equal to 6. That's why here 4d orbital has more energy than 4s orbital. So statement, among the two orbital, one orbital having higher value for n plus L has more energy. Let's say among 4s and 3d, 4d has more energy because n plus L value for the 4d is more. Okay, so another example 3s orbital and 3p orbital, which is a more energy. Here 3p is a more energy. It's decided on the basis of n plus L rule. For 3s, n equal to 3, L equal to 0. So n plus L is equal to 3. For 3p, n equal to 3, L equal to 1. So n plus L is equal to 3 plus 1 is equal to 4. That's why 3p has more energy than 3s orbitals. So this is called n plus rule. But some case what happened actually, the n plus L value for the two orbitals are same, some cases. For example, if you take example 4d orbital and 5p orbital. Suppose if you take this example. Here n value equal to 4, L value is equal to 2. 5p, n is equal to 4, 5, L equal to 1. So n plus L is equal to 4 plus 1 equal to 6. Here n plus L, again here also 5 plus 1 is equal to 6. But now among a 4d and 5p, which is a more energy? Now this is decided on the basis of the principal quantum number n value. Those orbital having higher value for n, that has a more energy. Here 5p has higher value for n, that has more energy than 4d orbitals. Okay, so here 5p has a more energy than 4d orbital. So this is the second statement. If n plus L values are the same, then the orbital having higher value for n, that has more energy. Okay, one more example, 4f orbital and 5d orbital. Suppose 5d orbital. Okay, this one, n equal to 4, L equal to 3. So n plus L is equal to 7. Here n equal to 5, L equal to 2. So n plus L equal to 7. Which is higher energy? 5d. 5d has more energy than 4p orbital, because for a 5d orbital n value is a greater. Here n value 4, here n value 5. Okay, so n plus L values are same, but those orbital have a higher value for n, that has a more energy. This is the second statement of the n plus L rules. Okay, next about the max stability of the completely and half filled orbital. We know that completely filled and half filled orbitals are the more stable. Okay, why they are more stable? So one of the reason, they are symmetrical distribution of electron takes place in case the half filled and completely filled. So one example, manganese. Manganese atomic number is 25. So its configuration is 1s2, 2s2, 2p6, 2p6, 3s2, 3p6, 3d5 or 4s2, 3d5. Here half filled orbital, 3d is a half filled orbital. Just observe here, in this case d orbital, there are 5 orientations are possible. This is the 5 orientation, but all electrons have singly occupied, but with symmetrical distribution. All electrons spin are same direction. Okay, the symmetrical distribution of electron takes place in the d orbital. Due to the symmetrical distribution of electron, half filled orbitals or a completely filled orbitals are more stable. But suppose orbitals are not completely filled, are not completely half filled. In such a case, symmetrical distribution not observed. That's why its energy is stability is less. Second one is exchange energy, maximum exchange energy. Suppose D5 system, if you consider, same example I consider, manganese, atomic number 25, its configuration I can written as argon, 3d5, 4s2. So here this is 18 argon, this one here 18. So 3d5, here say how many maximum exchange, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So now I named as this one orbital 1, 2, 3, 4, 5 orbital. So what happened here actually, the first electron can pairing with the second electron, or first electron can pairing with the third electron, or first electron can pairing with the fourth electron, or first electron can pairing with the 5 electron. So 4 exchange energies are possible with the first electron. Second electron can pairing with the third electron. Second electron can pairing with the fourth electron. Second electron can pairing with the fifth electron. Totally 3 maximum exchanges are possible. Go for the third electron. Third electron can exchange with pairing with the fourth electron. Third electron can exchange with pairing with the fifth electron. So that's why 2 exchanges are possible. Last fourth electron. Fourth electron can exchange with the fifth electron. 1 possibility. Totally 4 plus 3, 7. 7 plus 10 exchanges are possible. Maximum exchange energies are possible. During this exchange, pairing of electrons, some amount of energy liberated. This is called exchange energy. Maximum exchange energies are possible if orbitals are half filled or a completely filled. Suppose if you consider D3 system, D3 means there are 3 electrons present in the d orbital. 1, 2, 3, 4, 5. So 1, 2, 3 is a present. How many exchange energy? 1, 2, 3. So first electron can exchange with the second one. First electron can exchange with the second, third one. 2 exchange. This one, second electron can exchange with this one. 1 exchange. Only 3 exchanges are possible. Less number of exchange. Okay, so half filled and completely filled has a maximum exchange energy. That's why its stability is more. Totally half filled and completely filled orbits are more stable because of the 2 reasons. One is a symmetrical distribution of electron. Second one is a exchange energy.